Hi there. Today we're going to take up the resistive and inductive parallel circuit. We're going to go through some of the preliminary rules that are going to help guide us in our strategies to solve for the missing values that you see before you. We have an applied voltage of 110 volts at a frequency of 60 hertz, which is the North American standard. We have this resistive branch with a resistance of 57.1 ohms, as well as I have this inductive branch with an inductive reactance of 85.7 ohms. I'm going to show you the strategies used for solving for all of the missing values here that we have before us. Of note, we'll be solving for the apparent power of the circuit, the efficiency of the circuit, or otherwise known as power factor, and angle theta, where we're going to start talking about the phase angle difference that exists between the voltage waveforms of the input voltage and the current waveform. Now, we're going to refresh our memory about what are some of the rules, or the three basic rules, that will govern how we approach solving for the missing values. When it comes to the voltages, if two or more electric components are wired in parallel, the common voltage will appear across all branches of the circuit. That is to say that the input voltage of 110 volts will appear across the resistive branch as well as across the inductive branch. In a simple parallel circuit, the total current will be the sum of the individual currents of each of the branches. So that's going to be pretty straightforward. Where I anticipate where most people have a problem with is trying to solve for the overall impedance of the circuit. Due to the fact that when we start talking about a parallel circuit, the overall impedance will be less than the smallest value of resistance, or in this case, inductive reactance. My prediction then is that the overall circuit impedance is going to be less than 57.1 ohms. And we're going to see if that holds true. So let's take out our pens, pencils, and grab a sheet of paper, and let's dive into this. Step 1, calculating the circuit impedance. Now, we're working with a parallel circuit, and there's going to be some slight modifications. Before, when we worked with a series circuit, to find the impedance, we just took the value of resistance squared plus the value of inductive reactance squared, square root, and we got a value for impedance. But with the parallel circuit, we know through studying Ohm's law that the overall resistance of the circuit will be smaller than the lowest value of resistor. Now, what we have to do is we actually have to combine both of these formulas into one formula. And that formula is going to look an awful lot like this. Z is going to be equal to 1 over R squared plus 1 over X sub L square square root and then 1 over. I will be doing a detailed procedure of how to enter this formula into a calculator. Now, moving on from this, I'm going to move down the board, and we're actually going to put in our values and solve for the value of circuit impedance. Now that we have our formula, I'm going to move down the board, and I'm going to put in our actual circuit values, and we're going to solve for the value of circuit impedance. Now, I've went ahead and I've wrote down the formula, but I've now used the actual values from our circuit. 1 over 57.1 ohms of resistance squared plus 1 over 85.7 ohms of inductive reactance. We will do the square root and then the 1 over. Punching this into a calculator, the results should be 47.52 ohms. Now, this has been rounded to 2 decimal places, and we're going to keep moving on at this point. Now, I've gone ahead and I've put in that value we've just calculated, the 47.52 ohms of impedance. I've also got the applied voltage. One of the rules that governs the parallel circuit is that the applied voltage will be the same at each branch of the circuit, meaning I would have 110 volts down this branch and 110 volts down this branch. So I could just as easily transpose this value over here. Now, I have 2 values that I can work with that I could solve for the remaining values that are missing here in this branch for the resistor. I could find the current as well as then I could find for the value of power. And so that's where I'm going to go. I will normally solve all of the missing values branch by branch, and then I will go and finish up for the entire circuit. So let's move on to step 2. We're moving to step 2, which is calculating the current draw from the resistive branch. Now we're going to use the Ohm's law triangle, where if I cover up I, which stands for current, you'll see that we're going to take the voltage across that branch and we're going to divide it by the value of resistance. That gives us the following formula. Now I've put the R as a subscript just to keep things clear in my mind so that I don't make any mistakes along the way. This is a lengthy process, and so a little bit of tidiness in my calculations helps pay off huge dividends. I don't make as many mistakes. So let's take the values. 110 volts AC divided by the value of resistance. Now that was 57.1 ohms. Type that into the calculator. You should have, as a result, 1.93 amps. Now that is rounded to 2 decimal places. Moving right along, we're going to go and jump to step 3, computing for the value of true power for the resistive branch. We're still using elements of Ohm's law, where the power is equal to the value of voltage multiplied by the value of current. So if we cover up the P, it's E times I. That gives us the following formula. P is equal to E sub R multiplied by I sub R. Let's input our values. And the answer should be 211.91 watts. True power is expressed as watts. Reactive power will always be expressed as VARs, volt amps reactive. So I'm going to go and input these values into my chart, and then we're going to determine where do we go from here. I've gone ahead and I've inputted the values we've calculated into the chart. You can see that this branch, all of the values have now been completed. I am now going to move on to the next half of my circuit, the inductive branch. I am going to calculate the value of current draw from the inductor as well as the reactive power. And while I'm at it, I'm also going to find the value of inductance of the inductor itself. So we're going to reset and we're going to jump to steps 4 and 5. Step 4, calculate the current draw of the inductor. You'll notice I still have the Ohm's law triangle here, but there's going to be a slight alteration. Because the fact that inductive reactance is measured in ohms, it's a simple matter of substituting the R for X sub L. The formula works in the exact same manner. And so, in this formula, we replace the R with X sub L. Inductive reactance acts the same way as a resistor. It serves to limit the amount of current flow in a circuit. So it kind of walks like a duck, it quacks like a duck, but it's not exactly a duck. It's a little bit different. Now, let's go ahead and input our values. "110 volts divided by the 85.7 ohms, and input that into a calculator. You should get, for an answer, 1.28 amps. Now, while I have this value still in the display of my calculator, I want to proceed to jumping to step 5, which would be to calculate for the value of reactive power using the applied voltage and the current. So I'm going to be right back. Now, step 5, compute the value of reactive power. You'll notice I've still drawn the Ohm's law triangle, but where we used to have a P here, we now have the value of VARS L. Reactive power apparent power, true power, reactive power. They are all considered power, and the value or the expression is interchangeable. I could put in here a P, VA, or in this case, VAR sub L, and the formula does work mathematically. Here, we're going to take our applied voltage and the current we just finished calculating. We're going to input it into this formula, and we're going to see what we're going to get as a result. And you should, if you're accurate with your calculations, end up with 141.19 VARS sub L rounded to 2 decimal places. Let's proceed to filling in the chart. We also have to calculate the value of inductance. Here, I've gone ahead and I've inputted all of the values we've calculated in red. You'll notice I have one value remaining, and that is the value of inductance. What is the formula to use to find inductance is derived from this formula for inductive reactance, which is simply 2 times pi times the frequency times the value of inductance. Now, 2 and pi are given values. They do not change in the formula. But I'm going to have to manipulate this formula to isolate for the value of inductance. And so, L will be equal to X sub L divided by 2 times pi times the frequency. So let's input our values. .7 ohms times 2, or divided by 2, times 3.1416 times a frequency of 60 hertz. Now, don't forget if you're attempting to put this into your calculator as a single equation, your PEDMAS rules to use brackets. If you've done this successfully, your answer will end up being 0.23 henries. And the value of inductance is expressed in henries, and this is a value that has been rounded to 2 decimal places. So let's input that into our chart. Now that I've calculated all of the missing values for the circuit itself and in the individual branches, the inductive branch, the resistive branch, all that remains now is to solve for the entire circuit. So we're going to be moving on to steps 6, which will be finding the total amount of current for the circuit and then the amount of apparent power for the circuit. So let's move over down to the next board. Our next step, find the value of circuit current. Now I've drawn the Ohm's law triangle, and if we're looking for current, we're simply going to use that age-old trick where we cover up the I and we see that we're going to need to take the applied voltage and divide it by the impedance. That's going to give us the following formula. I total is equal to E total divided by impedance. So if I go ahead and I input the values that we've already calculated and the given value of the input voltage, I'm going to get I total is equal to 110 volts AC divided by our value of impedance, which we've calculated at 47.52 ohms. Input these values into a calculator and you should be getting for a result 2.31 amps, and again this is rounded to 2 decimal places. So we're going to input this into the chart and we're just going to keep moving along. Now step 7, solve for the value of apparent power. So this is the total amount of power consumed by the circuit. It's going to involve elements of true power and reactive power. So that's where the name apparent power was derived from. Now we can use one of 2 methods, Ohm's law or a trig formula. I'm going to be doing both because I like to prove beyond a shadow of a doubt that the math works. Ohm's law, simply, VA is equal to the applied voltage, or E total, multiplied by I total. 110 volts multiplied by the current we've just finished calculating, 2.31 amps. And that is going to give you 254.1 VA. Now that's just using Ohm's law. We can also do it using the trig formula. The trig formula is based off of VA is equal to P squared plus vars L squared square root. Now, regardless if the circuit is series or parallel, this formula remains the same. We're using our values, 211.91 watts squared plus 141.19 vars L squared square root. You'll end up, if you've done the work accurately, 254.64 VA. You'll notice there's a discrepancy of about 0.5. Overall, that represents less than 1% of error. So for anybody doing the calculations at home, everything works out mathematically. Why there's a discrepancy is because all throughout the process, we've been rounding to 2 decimal places, and this would account for why we're not exactly as accurate in our finished product, but we're extremely, extremely close. So let's move on to back to our chart, and let's fill in these values we've calculated. I've inputted the remaining values for the entire circuit. So we now have the total amount of current the circuit was drawing, and we've calculated the apparent power. What remains now is to calculate the power factor of the circuit, or in other words, the efficiency of the circuit. And we'll also calculate angle theta. And just as a reminder, what is angle theta? Well, angle theta is the actual measurement or the phase angle difference between the current waveform to the voltage waveform for the entire circuit. So that if I actually went and built this and we measured it, I would be able to use an oscilloscope and physically measure that difference. It's going to tell us how accurate things are. So let's move on down and get busy calculating efficiency. Step 8. Calculate the efficiency of the entire circuit by finding your power factor. Now, power factor is based off of a ratio, and as such, there's many different formulas that we could use to apply it using the values in the circuit. I could use power divided by VA. I could use the value of impedance divided by the value of resistance, or I could use the current draw across the resistive branch divided by the current draw of the entire circuit. How I've always remembered it is simply, and this is what works for me, power factor is the ratio of true power to apparent power. Reason I like this formula is because regardless of the circuit I am working with, the values never change. So you work with power, your work will always be accurate. This formula only applies to the parallel circuit. If you were to try and do this using the series circuit, the formula does not apply, it will not function. Same thing over here. In the series circuit, will the current's the same at any point in the circuit? This formula will not apply to a series circuit. It only applies to a parallel circuit. And it's for that reason where I tend to shy away from these formulas, and they're best left in the textbook. Because I like to be accurate, and I want to, I apply the KISS principle. Keep it simple, surge. So let's go with this formula. It's put in the values that we've calculated, and that would be 211.91 watts divided by the 254.64 VA we had just calculated. And you should take this value, because power factor is expressed as a percentage, we're also going to have to multiply this by 100. You should end up with 0.8387825457 multiplied by 100, and your expression should be 83.88%. And I'm going to erase this, and I'd like to jump to the last step, which will be to calculate angle theta. Our final step, determine the value of angle theta. As I said earlier, this is a really important step, because if we built the circuit, it's going to allow me to take a measurement of the phase angle difference between the voltage and current waveforms using an oscilloscope. And that's for the only reason students are required to do this calculation. Now, I would still have this value in my calculator. I know through years of experience that if I was just to multiply this, I don't physically do it. I just move my decimal place 2 spaces and I do the expression. But I can take this value and input it directly into this formula. Now this formula needs to be manipulated a little bit because I want to isolate for angle theta. That means then that angle theta is going to be equal to the power factor. Now we're going to use not the percentage but the actual decimal value, and we're going to multiply it, or we're going to use the negative cosine function on our calculator. So angle theta, we're going to use 0.83, and I'm going to round this to 4 decimal places, 88. Then we'll hit negative cosine in the calculator, and as a result, angle theta will be 32.99 degrees. Now, angle theta is expressed in degrees, and there you have it. We have completed all the values for this circuit, and what we have to do now is explain the voltage and current relationship for each of the branches, as well as draw it in for the total circuit. Here we have in front of us 3 oscilloscope displays. Because this is a parallel circuit, and one of the rules that govern a parallel circuit is that the voltage is the same at any branch of the circuit. And as such, I've gone ahead and I have drawn in a blue waveform to represent the voltage. And you'll notice that the waveform is identical in each of these displays. XL is going to represent the inductive branch, R will represent the resistive branch, and Z will represent the total circuit. Now I'm going to use red to indicate the current relationship. Now here across the resistive portion of the circuit, voltage and current are in phase with one another. And what that means then is that if they're in phase, both of the waveforms are going to start at the 0 section. They will rise in unison, collapse in unison, cross over at the median, and complete the negative alteration in unison. Now, because of the fact that I'm doing this with a color magic marker, people would be able to distinguish between the voltage and the current. But if you're using a pencil and somebody's going to grade your work, they need to be able to distinguish between the two. So it's important that we label everything. And so I'm going to put an I to make sure that people understand and are able to distinguish what represents the voltage, what represents the current. Now here, for the inductive branch, inductors oppose a change of current. Now if the voltage is the same and the inductor naturally opposes a change of current, then that means that the current is going to lag the voltage waveform by 90 degrees. Now this is something that is standard in a textbook. Now that means then that if this voltage waveform is at 0, then the current is going to be down here somewhere because it's going to be lagging, and by 90 degrees. This is 180, here is 360, so halfway in between is 90. So we're going to come down here, and then where we're at our peak, the current will be at 0. When the magnetic field of the voltage waveform starts to collapse, this will start to gain strength and will peak when the voltage waveform is at 0. And then as this waveform goes into the negative alternation and the continually expanding magnetic field is starting to gain strength, the current waveform is going to lag behind and it starts to drop. And it'll cross over at roughly 270 degrees and continue on this same pattern. We are going to identify it. And what we're going to do as well is we're going to explain that relationship. On tests, I give points to students who will draw this out and then explain the relationship. What they are going to be expected to do is explain that the current lags behind the voltage by 9 degrees. Now, the same cannot be said if somebody was to say the voltage leads the current by 90 degrees. Because of the fact the voltage is something that is stationary, it can't move. And the grammar does not make sense. You have to say the current lagged behind the voltage by 90 degrees. Now, here we would say voltage and current are in phase with each other. Now, it doesn't matter if you say current and voltage are in phase with one another, because of the fact that they are in sync with one another. There's no proper grammar here or an issue with it. Now, up here for the entire circuit, I know that the circuit was comprised of resistive and inductive components. I know that the voltage and current are not going to be in phase with one another, but I know that the phase angle difference between them isn't going to exceed 90 degrees with the current lagging. It's going to be somewhere in between. It was based on the ratio. And that's why we found out angle theta. Angle theta mentioned that we were out by 32.99 degrees. Well, here is 180, 90, split the difference, that's 45, so I'm in here somewhere. Now, just like here, the current is going to be lagging, so somewhere about here, I'm going to draw that out. It's going to come down right about there, and that's how I'm going to draw my current waveform, and then it'll come up this way. I'm going to identify it, and I'm also going to write it out that the current lags the voltage by the angle theta, which in this case equals 32.99 degrees. Typically, on one of my tests, I will give a student the calculations, and that usually is worth about 6 points, with 4 points attributed to here, on average. No, it'll usually be about 3 points. 1 point for the actual diagrams, and then 1 point for explaining it. So it is particularly of value to make sure a student understands these aspects, as it will help them on their future evaluations. Stay tuned. I have another video where I'm going to be building this very same circuit, and we're going to feature using an oscilloscope, and I'm going to use a projector to show people that the calculations we've done here today are indeed accurate, and they will work out in real life. I've hoped you found this information helpful in your study of electricity, and please subscribe to more of my videos. Until next time, stay safe.